All right, well, good evening and welcome to lecture 22 of MT225. Uh, this is our, let's see, this is, I think, our next to last official class, I suppose, with new material anyway. We'll be finishing up this week on stresses and strains. Next week, we'll be focusing on materials and bending of beams, and then we'll be having our prep for our final exam. So 2 weeks from tonight will be our final exam, same format as the second exam that we did. I'll post it, and it'll be due by midnight that night. So let's see here. Administrative notes, the schedule for the remainder of the semester I posted in the last set of notes. So if you don't have that or haven't looked at it, check out lecture 21. That has the schedule for the next 2.5 weeks, I suppose. Homework 9 has been posted. That's due next week. It's our last official homework assignment. You'll find it to be quite a bit simpler than the truss analysis problems. Literally, like I said last time, the hardest part about the current stuff we're doing is making sure you know how to calculate areas. So that's the focus there. We'll review a little bit of what we did on Wednesday or on Monday night. But that's due next Wednesday. Tonight, we're going to review normal stresses. And so we'll go through another problem where we'll practice a little bit on finding out normal stresses and deformations that result from it. And I'll show you the equation that you can use to jump straight from the amount of force to the amount of deformation. Then we'll take a look at shear stresses. Now, most of you are from an aviation background, and I think everyone who is in that group has dealt with rivets. The whole purpose behind a rivet in most applications is to resist or apply shear stresses. And so shear stresses are huge, and they're of extreme importance in aircraft applications, which is one of the reasons I cover that a little bit more in detail than a typical strengths class would do. So we'll be taking a look at shear stress tonight. We won't really be looking much at what we could call shear strain. There is such a thing, but it's not nearly as important as normal strain. So we're much more interested with just the stresses that happen in shear. So let's review normal stresses. So the picture from last time was let's see here, was a beam. So if we have a beam under tension, and it could work whether it's in tension or it's in compression. We can have tensile stresses or compressive stresses. I described it last time all in tension, but that's because it's easier to draw. In the example we'll do this evening, we'll work out one in compression and see how the compressive stresses work out. Here's a beam under tension. We put some load on it. Let's say 30 kips. So if there's 30 kips pulling on the left end of the beam, there better be 30 kips pulling on the right end of the beam too, or this thing isn't in equilibrium. So we've got 30 kips acting on this beam. This beam is in tension, and it carries a load of 30 kips. If we cut through the middle and just isolate the left-hand side, we have our 30 kips, and then we've got where we cut the beam. Where we cut the beam, we don't have a point force. We don't have a force exerting on a single point. Instead, we have a force that is distributed, that is spread out over the cross-sectional area of the beam. If this piece of the beam is in equilibrium, and that's a fundamental idea that we've had since the beginning, that if a structure is in equilibrium, every piece of it must be in equilibrium. If this part to the left here of my cut line is in equilibrium, then whatever this adds up to must be 30 kips. What it ends up being, as long as we're far away from the ends, is that force of 30 kips is spread uniformly across the area. So if we have, for example, some shape, and it really doesn't matter the detail of the shape as long as we can figure out what the area is. It's going to have some area A to it. The force spread out over that area A is what we call the normal stress. We use the Greek letter sigma for that. The normal stress is the force spread out over the area. Now that only works as long as that force is uniformly spread out. Down here at the end, we don't have a uniform spreading of force, so we really can't say what the stresses are down here. But we can say down here in the middle of the beam where the area is, where the force is distributed uniformly over the area, that we have a nice normal stress. And that normal word, again, just to remember the terminology, normal refers to perpendicular. In this case, perpendicular to this exposed surface of the beam. So that's our normal stress. Because we're dealing with typically pounds or kips of force and square inches of area, our typical units for stress are PSI or KSI, pounds per square inch or thousands of pounds per square inch. The way I like to think about stress is an internal reaction to an external force. It's how the system responds at the molecular level, essentially, or at the grain level in the metal, to externally applied loads. We've got these external forces. The material has to be able to generate an internal response to that to balance off those forces. And that internal response is spread out over an area. That is our stress. Now, the smaller we make this area, the higher the stress becomes. And last time we talked a little bit about the fact that stresses in materials have limits. Each material has a yield stress and an ultimate stress. If this area is somehow reduced, then the stress that is encountered in the material is automatically higher, even if the forces are, are the same. Take, for example, let's say we've got this beam, but this beam has a crack in it. If this beam has a crack in it right there, there's a portion of this beam where the area is much smaller than the cross-sectional area of the beam. Could be a lot smaller. In that area, the stress is going to be a lot higher. Over here where the beam isn't cracked, it's going to have a nice uniform distribution of force. But if the beam is cracked, then there are parts of it not making contact. Only a smaller area is going to be holding against that force. So you have the same force on a smaller area. When that denominator gets smaller, the stress gets bigger. This is why, as it happens sometimes in structures, you get a little crack started, and then it tends to run. It tends to keep going because once that crack starts, it locally raises the stress, and then the material is less able to handle it. So the material has more stress. It breaks even further. The crack propagates. It travels across, and eventually it ends up breaking. One of the things that Boeing did very early in their design and trying to make sure that aircraft had a lot longer lifetime than the aircraft at the time were to add essentially doublers, add extra material in areas that were prone to cracking, so that there was something else there that normally wouldn't be handling stress. But if the structure were to become compromised, those what they called tear stoppers or crack stoppers would take on that extra stress and prevent the crack from growing. So normal stress, pretty important idea there. What the limits are will depend on the materials, and we'll take a look at the details of different materials next week. So that's our normal stress. Stress causes the bonds in between the molecules that make up the material and the grains that make up the material. It causes those to change shape. Each inch of material deforms a little bit under stress. Now, if that's a tensile stress, then the material expands a little bit. If it's a compressive stress, where the force arrows here are pushing in instead of pushing out, then it's a compressive stress and the material shrinks a little bit. The amount of stretch or shrink is determined by properties of the material. It has everything to do with the details of the grains and the molecules and atoms that make up that individual material. Essentially, it has to do with how stiff the material is. And the number that tells us how stiff a material is, how much it will tend to change under stress, we called the modulus of elasticity. We gave it the letter E. That was our modulus of elasticity. And that's typically also measured in the same units of stress. So things like KSI, or sometimes, because it can be very large, things like MSI, millions of pounds per square inch. So this is a big number typically, which means that in order to get even a little bit of change in shape, a little bit of deformation, you need to have lots and lots of stress. We had a relationship between stress and strain. We had one more symbol here, the strain. That was our little Greek letter epsilon. Strain is the amount of deformation. It's how much each unit of length increases or decreases by. So if it's a tensile stress, we'll get a tensile strain, we'll get a stretch. Each inch will become something a little bit bigger than an inch. If it's a compressive stress, then each inch will become something a little less than an inch. Strain is the amount of deformation that we have relative to the overall length of the material. And so that means that the strain is a ratio, and strain is dimensionless. No units on strain, or at least units that would cancel each other out. So the one we typically go with are things like inches per inch. So that means each inch is magnified by a certain factor in inches. So each inch becomes something a little bit bigger, a little bit smaller in inches. So it's how many inches per inch of growth, or of reduction in size. And because it's dimensionless, any ratio or any unit that does that would work for us. We could do feet per feet, inches per inches, meters per meter, mile per mile, all of it work. Well, strain can be calculated from the stress. We saw that last time as what we called Hooke's law. Hooke's law says that the amount of strain that we get is equal to the amount of stress divided by the modulus of elasticity. That is Hooke's law. This one's the only, I suppose, rule of nature that is involved here. Everything else is a definition. We've defined the normal stress to be the force spread out over the area. We've defined the strain to be the relative deformation. We've defined the modulus of elasticity really through this law of nature. This is roughly similar to something like Newton's second law. It's a way of describing how a system reacts when you put forces on it. In this case, it says that when we apply a force, we're going to get some amount of deformation. How much deformation will depend on how stiff the material is. If the Young's modulus is very high, meaning we have a very stiff material, then even if we put a lot of stress on it, we're not going to get very much strain. On the other hand, if we've got a more plastic material, a material that doesn't tend to be very rigid, that can stretch fairly easily, the modulus tends to be low, so we're able to put a good bit of stress on it and get a lot of strain. So Hooke's law is kind of a fundamental rule of nature, or at least it's based on the way that we see materials behave. Just like Newton's second law was based on how people observed motion to happen, Hooke's law is based on how people observe materials to behave. And we'll see on Monday that the reality is a lot more complicated than this pretty simple relationship, this nice proportionality that we've got. that in reality there are a lot more details to it. But as long as we stick with relatively low stresses, this is a pretty good model. It's just like just like Ohm's law. Ohm's law works well as long as you don't push it too hard. If the voltages are low enough and the currents are low enough, things work great. You start trying to push a million amps of current through something or put 10 million volts on something, things tend to change in ways you don't expect. So the basic simple rule breaks. Now, last time we put these all together into kind of a little loop that I drew out, and I'll try to draw that while leaving the fundamental components still on the display. We started out with force. Everything we've done up to this point has been about trying to find the forces. What force is acting on each member, what force each member has to handle. That's an external uh, picture. It's something we see from the outside. To get into the internal response, what happens inside the material? So that's internal or the material. To jump into the material, we have to turn the force into a stress. And the way we turn a force into a stress is by using the definition of stress. Stress is force divided by area. So by dividing out the details of the shape or the details of the cross section, we're able to figure out this internal factor. And last time I mentioned that internal factor, that stress, is a huge simplification. It lets us only really have to list in a reference somewhere what the limits are on the material. We don't have to consider anything about the shape because the shape has been divided out. If we didn't have this, then we'd have to have a big table somewhere that says, well, for a beam made out of aluminum that's 1 inch by 1 inch, the amount of force that it can handle is this amount. Let's say 2,570 pounds. Well, for a 2 inch by 2 inch, now that can handle, let's say, 6,000 pounds. And we can go and we'd have to tabulate all of those. And that would be a real pain. We'd have a huge table to deal with. By dealing with just the stress, we take away the details of the shape. We've encoded them in the stress already. And all we have to do is know whether that stress is up near the limit or not for that material. So that's a huge simplification. It makes our lives a lot easier when we start designing things. Now, to get to the deformation, to get to the strain, we can use Hooke's law. So we can jump from the stress to Hooke's law by using from the stress to the strain by using Hooke's law. Strain is the normal stress divided by the modulus, and that's a material property. So you can go to a table and figure out what that is. We can measure that area. We can look up based on the material what the modulus is. And then we had our elongation. Suppose that's one I didn't write over here. Elongation is what we get when we add up the stress over the entire length of the member. So elongation, that's typically in things like inches or feet. It's a length. Since strain has no units, all it does is tell us how much each inch grows. If we multiply that by the number of inches, that tells us how much overall growth we've got. So we can get from our strain to our elongation, which is another external property, something we could physically measure, versus something that's happening inside on the material level. We can calculate that with delta equals epsilon L. Now there is a way to jump straight from the external quantity force to the internal, or to that external quantity, that deformation. And what it really does is it involves plugging all of these equations together. You could say, well, the elongation is epsilon L. Well, epsilon is sigma over E, and sigma is F over A. And if you work through all that algebra, you get an equation that says that the elongation is F times L over A times E. And if you look at what you've got here, and I'll leave that as a challenge to you to work out the algebra on that and prove that if you plug all these equations together going the long way around the loop, you end up with that same equation going the short way. FL over AE takes our force, which is our externally applied load, and it multiplies it by properties of the beam. Geometry, the length and the area, and material are both in here. E is always about the material, whether it's aluminum or titanium or steel or southern yellow pine. Area and length, those are dimensional factors. Those are things we could measure about the geometry. So it's geometry and material that turns force into elongation. Now, this is nice as far as doing a quick calculation goes. You do have to be careful about units. Force is typically in either pounds or kips. You've got to have your modulus in corresponding units. So if you have kips up here, you've got to use KSI down here. If you've got pounds up here, you got to use PSI down here. The area has to be in square inches. It won't work if the area is in isn't in square inches, since typically the modulus involves square over square inches, PSI or KSI. The only one that has units that really aren't going to matter directly is the length. Whatever units you have on the length, it'll be the same units for the deformation. So if you plug in a length of inches, you'll get inches out. If you plug in a length of feet, you'll get feet out. But area has to be in square inches. Elongation, or the modulus, has to be in corresponding units to the force. I tend to like to go the long way around because right here, when dealing with that stress, you can check and make sure you're not violating a limit. It's pretty easy when you're just plugging together numbers to see what the elongation would be or what the deformation would be, to not realize that you've actually taken the stress in the material way above the limit. You've plugged in too small an area, and you end up with stress that is unreasonable, and you'd never really get this elongation because the part would break well before you'd ever get there. I like to figure out my stress first, make sure that stress is reasonable and within the right range. It has to be low enough in order to make this Hooke's law something reasonable to apply. And the details of that will make a little more sense after we talk about the details of materials on Monday. But for the most part, I think the sequence of three shorter equations versus plugging everything together, I like going the long way around. But in the end, as long as you get the right answer, I suppose it's fine. But I think this path here is a little more fraught with difficulty because you could pretty easily miss some clues that you have violated some assumptions or you're pushing the equations too hard.
So what's the advantage to using this shorter method then?
It's quick.
That's
If you know
okay.
you're dealing with stresses that aren't going to be in the in kind of danger zones around where the limits are for the stress on that material, it's not a bad way of kind of closing in on the details of what kind of elongations you're going to look at.
Okay.
But it's not the kind of thing you typically do for a first pass. If you've figured out the load on this beam and you want to make sure, well, I want to make it out of 2 inches by 2 inches aluminum. Figure out the stress first, make sure that stress is safe. Then you can go and plug it all in and make sure the elongation is good. Maybe the elongation you get's too much. So you need to lower the stresses by either increasing the area or maybe shortening the beam if you can, or going with a different material. But it gives you a starting point, and then you can play with it a little more quickly with that equation. But it's personal preference, whichever way you'd like to go. But just be aware that it's easy to miss some important things if you just jump straight to that.
Gotcha.
All right. So let's do an example here. Let me see if I missed any points in my slides here. So normal stress, normal strain, Hooke's law, modulus of elasticity, and talked about the units. So they're all there. Normal stresses perpendicular to the surface, and we'll come back to shear stresses here in a second. So let's do an example. So let's take a beam. Last time we worked through a number of different examples in the practicum session of using different areas. We're not going to get too sophisticated here. I just want to work out the basics of it. So let's take a beam here, and I'll draw the cross section over here. We'll make it a rectangular beam. How about, I've been working with framing members all day, so we'll make it 3.5 inches by 1.5 inches. Those of you know about a little bit about wood framing know where I'm going with that one.
That's a 2x4.
It's basically the 2x4, although they've been shaving off an extra 1/16 of an inch for a while now.
Yep. Yeah. OSB is doing the same thing.
Yep. Yeah, and I've got
1930 seconds.
Yeah, in this place, I've got a bunch of old dimension lumber too, so it's 1 5/8 inch thick.
Ah.
So that's fun to try to frame in, try to match up something to. So we'll take this piece here, and we'll put a compressive load on it this time. So we'll put a compressive load on. Doesn't really change anything in terms of our analysis, just how we report our elongation, because it really isn't an elongation in this case, it's a shrink. So we'll see how that works out here. Let's put 20 kips on this. And we'll make it out of, let's make a titanium 2x4 here. And if I go to my reference book here, titanium has a modulus of elasticity of 16 MSI. So the modulus of elasticity is 16 million pounds per square inch. So it's pretty stiff. It's not something that responds a lot to load. So let's first figure out our stress here. So first step, we'll find our stress. The normal stress is the force spread out over the area. We've got a force of 20 kips. We could go off to the side here and figure out our area. Area is length times width. It's just a rectangle. And if we multiply that out, we got 1.5 inches times 3.5 inches. That's 5.25 square inches. So that'll give us our stress. 20 divided by 5.25. We have 3.8095 kips per square inches, and that's KSI. Now I like to pause there and make sure that that's a reasonable stress to put on this kind of material. For titanium specifically, the stresses that titanium can handle are pretty huge. And in fact, for titanium, we're looking at about stresses that we'd have to worry about would be up in the 60 to 70 KSI range. So we're well below that. Now, most of the time, stresses that are quoted in references are tensile stresses. This is compressive, because one of the things we'll look at next week is how things fail. And when we pull on them hard enough to reach that maximum stress, that's when things tend to break. We tend to, on compressive stresses, we tend to have materials fail by buckling, meaning that it doesn't fracture. It tends to kick off to one side or the other and change its shape that way. We're going to assume our stress here because buckling is very difficult to analyze, well beyond the scope of this class. So we are going to assume that stress is low enough to make sure that this isn't really close to buckling. So that's our stress. Let's look at our strain here. Strain is how many inches each inch deforms. And yes, it was when I was looking in my book. Sorry about that. The strain is how much each inch changes shape, whether it shrinks or stretches, and whether it's how much factor each inch grows or shrinks by. So we'll find our strain next. Strain is stress divided by the Young's modulus. And so we've got to watch the units here. Got to have the same units in the top and the bottom. We're applying 3.8095 KSI. Our Young's modulus is 16 MSI, but if you just blindly divide this by 16, you're going to, and then ignore the units, you're going to end up with a huge number for the strain. We have to plug in KSI. This is MSI. From millions to thousands, you've got a factor of 1,000 there. So that's 16,000 KSI. Just like I've told you probably as long as you've known me, let the math tell you when to cancel the units out. Don't do it on your own. Don't just ignore them and assume they cancel out. The math will tell you when it cancels out. So we can take our 3.8095 and divide it by 16,000. And that tells us that we get a stress of a strain, excuse me, of 0.002 3809. Now there are technically no units on that, although it's not wrong to write something down like inches per inch or foot per foot. Something we do have to be careful of here is that this is a shrink. This is a ratio that is decreasing the size of things. What it really says is that each inch shrinks by a factor by about 238 millionths of an inch. And to show that that's a shrink, that it's a reduction in size, we throw a negative sign in there. Negative strains mean that the object has shrunk. Positive strains means that it's grown. And that'll reflect here in our elongation. When we find that elongation, we're multiplying the strain, how much length change there is on each inch or each foot, times the number of inches or feet we've got. So let's say this thing is relatively small, 4 feet long. We're okay plugging feet in here. We don't have to plug inches in. Whatever units you plug in for your length will be the same as the units for the elongation. People are just more used to thinking about things in inches instead of feet, especially when it comes into small values like thousandths and millionths. It's a lot easier to think of those in terms of inches. So it's usually your choice on what to plug in for the length. Here, I'm going to convert mine right away. I've got a strain of 0.00023809. Here, I'm going to convert it to inches, so I'll leave the inches per inches there. And I've left it negative. That'll make my elongation negative. That tells me how much this beam is going to shrink by. And 4 feet would be 48 inches. So if I take that negative 0.00023809 and multiply that by 48, I get a negative 0.01142 inches. Now, of course, no one's going to measure something that is 4 feet long down to the 10 millionth, or down to the millionth of an inch. So it's not a bad idea to round this off to something like 3 or even 2 sig figs. Thousandths, 10,000ths of an inch, about the limits we can really measure with that physically without going to very expensive tooling. So rounding that down to something a little more reasonable. We can say that this titanium beam would shrink by 0.0114 inches, 11.4 thousandths of an inch. So a little bit less than a 64th of an inch or so. 64th of an inch is about 16 thousandths. So the little bit less than a 64th. Not bad over 4 feet, not under 20,000 pounds of force on essentially something that's shaped like a 2x4. That's the advantage of that relatively high Young's modulus, that it's not going to change shape very much. So there's an example doing some compressive work. Now, just to demonstrate it once here, I'll show how you can use that the single jump equation here. But before I do, any questions on any of those 3 steps there? If you wanted to jump in 1 step and you were certain that your stresses were okay, you could figure out the elongation by plugging in the force times the length over the area times the Young's modulus. But you've got to watch those units. If you're going to do this, make sure you plug the units in to the equation. Don't just plug the numbers or run into your calculator. You're asking for trouble. So I'm going to put in 20 kips for my force. My length, I'll go with that 48 inches because I want my final answer in inches for this one. The area was 5.25 square inches. And then I've got 16,000 PSI or KSI. And I'm going to write that as kips per square inch. And you'll see why I write that way in just a second. I want to write it that way to make sure that the inches squared cancel out here. My inches squared and inches squared should cancel out. The kips and the kips should cancel out. And all I'm left with is whatever unit I plugged in with my length. So if we plug the numbers together here, I get 20 times 48 divided by 5.25 and divided by 16,000. And that gives us our same number. 2 within that last digit, you get 0.011429 on this one. So that makes sense because we rounded off twice. We rounded off here in figuring out our KSI. Then we rounded off again with our stress. So we have a little bit more strain. So we have a little more round off error. You have to interpret into this one the sign if it's a shrink or a stretch. So we know we've got a compressive load here, so our answer is going to be negative 0.0114. So it gets us to the same place in the end. But a little more care has to be taken with the units, and you always want to make sure you're not exceeding critical stresses. Any questions there? All right, so let's look at shear stresses. Now, the deal with anything called stress is that it's going to be a pressure. It's going to have the same kind of form as a pressure does, which is force over area. What this really comes down to is direction. When you think about it fundamentally, you really only have 2 possible directions for things, at least 2 possible simple directions. You've got perpendicular and parallel. When you've got a surface, you can either be perpendicular to that surface or parallel to that surface. Everything else is just a combination of those 2. Perpendicular was normal. Parallel is what creates what we call shear stress. So shear stress is the stress we get when the forces involved are parallel to surfaces, not necessarily perpendicular to them. So when a loading force acts parallel to a surface, the stress that's generated there we call the shear stress. It's calculated in a very similar way to normal stress. There is a force involved. There is an area involved. The tricky part is figuring out what the area is. It's figuring out what area do I have to use or do I have to calculate to make sure that to figure out what my shear stress is going to be. I can give you a trick though that in a few minutes I'll give you that to help you visualize what that area is going to be and make sure you calculate it correctly every time. Now, shear stress is as important as normal stress in structures. Even in things like wood structures, houses, and so on, shear stresses can be pretty important. It may be a normal stress that, say, causes a structure to collapse under its own weight, but when you have things like wind loads, which we've certainly had over the last several days, we've had wind loads. Those tend to generate shear forces. They tend to generate forces that would tend to be parallel to a surface instead of perpendicular. In an aircraft, we use shear stresses as one of the main ways that we handle forces on the structure. Every single lap joint that we have between skin sections, between different parts of structures put together, anytime we've used a rivet, we are working with shear stresses. Rivets don't handle tension. Rivets aren't bolts. If you pull on the head of a rivet, it tends to come off. But it is a lot harder to shear through it, to cut through the diameter. And that's where the shear stresses that we generate on aircraft tend to be resolved. It's how we hold the structure together. So let's get a basic visualization here for what shear stresses are. Let's take a look at what's on the screen here. We've got two plates, and they are lapped over each other. Those of you who have done our sheet metal course are familiar with this. This is a lap joint. Now, typically, you do that lap joint, you drill some number of holes, and you install some number of rivets, possibly multiple rows and so on, to hold those two together. But there are lots of ways of fighting against the shear stresses. What's being shown is that we've got a force pulling to the left and we've got a force pulling to the right. And if this is an equilibrium, then these two forces have to be the same. What's holding this together is going to determine how much shear stress we're dealing with. And the simplest way to figure out shear stress, kind of the first basic example of shear stress, would be to consider gluing these together. If we coated the surface in between these two plates with glue, the entire contact area in between these two plates would be fighting against that shear stress. It would be what would be fighting against these external forces. If not for the glue layer here, if I've glued over this thing here, something like that. So if not for that glue layer, these two would fly apart. That means whatever force is being applied is being counteracted by this glue. So let's go over to the board here, and we'll draw a free body diagram. So here's the picture we had on the slides. We have two plates glued together in a lap joint. Let's put 10 kips on it. So there we've got 10 kips of force, and this is in equilibrium. There's a layer of glue right here. Well, think method of sections. If I were to draw a little bubble system boundary around just this top plate, the free body diagram of that top plate would look something like this. I'd certainly still have my 10 kips over here, but where this glue is, what I would see would be a bunch of little forces spread out over that entire surface where the glue was. That looks a lot like our beam picture from earlier this evening and from last time. With our beam picture cut through the beam, we had these little forces spread out over the surface area, but those forces were perpendicular to the surface. With shear stress, the forces are parallel to the surface. So if I can figure out how much area is involved here, so let's put some dimensions on this here. Let's say this is a 2-inch lap. And if I draw the top view here, little drawings review, need some hidden lines right there. Let's say this thing is let's say this is 3 inches wide and it's a 2-inch lap. It's this whole surface in between there that's covered in glue. And it's not an unreasonable assumption to assume that the forces are spread out uniformly in that glue, assuming we've done a good job of spreading that glue and all that. I don't know if you've done wood structures yet and all that, but when we do things like scarf joints, we have to be very careful about how you spread that glue. You can't just run a bead of glue down the middle and sandwich the two pieces together. You got to spread it out nice and evenly. So we have that force spread out over a larger area to lower the stresses. If we take our force of 10 kips and divide it by the area of 6 square inches, 2 inches lap by 3 inches of width, we'll get our shear stress. And the symbol we use for shear stress is kind of simple. It's just S with a little s. Why they do it that way, I don't know. They could use sigma s, I guess, but the sigma maybe is just a little too foreign on that. But typically shear stress is just SS. So shear stress is force divided by area. It's the same basic equation as normal stress, but there's a difference. The area is the area the force is spread out over in shear, parallel to that surface. So let's figure out the numbers here. We've got 10 kips spread out over 6 square inches. So we've got a shear stress of 1.6667 kips per square inch, KSI. Now, anything that changes that area is going to change that shear stress. If there's a void, for example, if there's an area that didn't get covered properly with glue, then we have smaller area, more stress. And there is a limit to the amount of stress that a glue can handle. In the documentation for the glue, you can typically find out something about the maximum stress that glue can handle. So that's our first picture of shear stress. It's force spread out over an area, but that force is spread out parallel to the area, not perpendicular to it. That makes sense so far? All right, so I'll assume so.
So you just pretty much, once you have that figured out, you're going to do business as usual on this, following the same pattern as before?
Well, yeah, pretty much. I mean, you could. In fact, this is actually a lot simpler. By one hand, it's by one argument, it's a little more complex. But by the other, it's a little easier. We don't have the simple elongation kind of idea that we'd had with normal stress. When you have shear stresses, things don't tend to stretch or shrink what they tend to do is deform in terms of their angles. So what tends to happen is you start out with something that's rectangular. If you put a shear stress on it, what it tends to do is make it do that.
Gotcha.
It tends to change the angle. So if you took that top and the top and the bottom, and you slid them against each other, it would tend to rack like that. And you actually measure shear stresses in terms of the angles. That's not terribly useful from a structural standpoint, so we just never really bother with it. The thing we worry about most with shear stresses is making sure that we can calculate how much shear stress there is, so we make sure we're well away from the limits on that material holding the plates together. So it's more of we're not worried about it deforming, we just don't want it to break. And
Gotcha.
we'll see that here in several of our analysis exercises later on. One of the things we'll take a look at on Monday is we'll look at figuring out how many rivets we need in a lap joint. Now, everyone who's done sheet metal has been through the calculations to figure out how many rivets of a particular type you need to have a certain lap joint. We're going to look at it from the point of view of shear stress, which is sort of ignored in the sheet metal calculation in the A&P program, but it's buried in there. It's just a bunch of numbers you plug together. But if you understand what's actually happening, it becomes a lot easier to figure out from a shear stress point of view.
Huh.
So that'll be something we'll be doing on Monday with that. For now, we're just going to calculate. We're going to focus on being able to find the amount of shear stress that we have given the situation. So 1.6667 KSI. Now, if that's too high, the only choices I have would be to either lower the amount of force or increase the area. If I could increase the area of that lap, I'd lower the stress. That's exactly what we do, for example, in doing glue joints with wood. If you remember with glue joints in wood, if you just have a butt joint like that, all your stress is on that area right in between there. And it's not too hard to cause that to break, to exceed the limits on that material. On the other hand, if you do what we call a scarfed joint, where you cut the material back at an angle, something like that, what you're really doing is just expanding the area that glue has to be on. So you lower the overall stress. Now, this is not a simple situation. This is kind of a combination between normal stress and shear stress. There's a component of each of them there, but it's something that is used pretty frequently in repairs and in other applications with wood when wood has to be glued together. Now, typically we don't glue a lot of things together in modern aircraft, but we do use similar principles on some of the older ones, like doing repairs to wood spars, things like that. So that's the idea behind shear stress. Now, if we're not using glue, then we're going to have some other mechanism to handle that stress. And if you think about what this would look like, going back to the glued example for just a second, think about what this would look like if it failed. If you pulled hard enough on it so it came apart at the glued surface, you'd see every square inch of that glue exposed. That's a clue as to what was fighting the shear stresses that were in the system. The area that becomes exposed when it breaks. That can be a useful way of figuring out what area is the important area in figuring out shear stress. So let's get rid of the glued joint and let's try something a little more practical for working with, say, metal. We have a bolted joint. So let's take a look at something like this. This is a really kind of simple example, I suppose. In reality, we wouldn't do it this way for a lot of different reasons. But here I've got those same two plates, but rather than using glue, I've gone and drilled a big hole through them and put a pin in between. Now that pin, if it's strong enough, it's made of strong enough material, it will be able to keep these two plates from moving. But the difference between this and the glued example is that these parts of the plates over here and over here that are away from the pin aren't really doing anything to fight the shear stress. So it's not always the overlap area that's important. Go back to that idea of what it would look like if it broke. If you pulled on this hard enough to break it, what would happen is this would shear through the middle of this bolt. The diameter of that bolt and the area of the circle that that bolt or that pin is comprised of, that's what's fighting the shear stress. So let's see what that would look like here on the in the calculation. Oops. There we go. So let's take our lap joint. We'll do our top view first here. And we're just going to put a pin right in the middle of it. And let's see, we had, this was 3 inches. This was 2 inches. So not to scale. So let's make this a 5/8 inch diameter pin. So the side view is going to look something like this. So there we go. So we've got that pin. And we'll put that same 10 kips of force here. Now all that 10 kips of force is trying to shear through, trying to cut through that diameter of that pin. Think about, for those of you who've been through sheet metal, think about what you were doing with the rivet shears when you had to cut a rivet down to size so you could install it. Basically doing essentially this. You had one plate holding the rivet, another plate that would push by it and cut through. It would exceed the shear stress of the limits on the material and break away part of it. Here we're going to assume we're staying below the limits on the material. The area is the important part here. This is 5/8 inch diameter. You've got to remember how to calculate areas. Areas of a circle be pi r squared. Radius would be 5/16 of an inch, so we'd have pi times 5/16 squared. It's not going to be a pretty number, but let's go ahead and calculate that. So we've got a fairly small area here, definitely less than a square inch. We've got 3067 or 680.
Tom,
Yep, go ahead.
is that 5/8 or 5/16?
It's 5/8 diameter. So when we go to the
radius squared. Okay.
Yep. If you prefer to go straight from the diameter, as long as you get the right answer, go for it. But I always do pi r squared rather than quarter pi d squared. So 0.30680 square inches. So a little bit less than a third of a square inch. Not a lot of area there. The shear stress is the force over the area. And we can go ahead and draw the free body diagram here of that top plate and see what it would look like. The free body diagram of that top plate, you've got your 10 kips here, and then you have in this little 5/8 inch circle, you have your shear stresses. That's got to add up to 10 kips. When you add up all those little arrows together, that's got to be 10 kips, but that's over a lot smaller area than it was in the previous problem. So we'd expect the stresses to be a good bit higher. So let's see what we've got here. We had 10 kips over 0.30680 square inches. That's going to be 32.595 kips per square inch. So that's what the shear stress is. Now, something that I'd be worried about in doing this kind of calculation is that shear stress safe? Is that going to be in the limits of the material I'm using? Now, if I know what this bolt is, then I can certainly ask that. On the other side of it, we can say, well, this is the shear stress I need. What material can I select that will be able to handle that? I'd want to pick a material that has an ultimate shear stress greater than 32.595 KSI so that it won't shear out in this particular application. Now, in aircraft, we actually purposely select rivets that are below the shear stress that we calculate, where the material's ultimate stress is below that. And those of you who've been through sheet metal remember the reason for that. It's a lot easier to make a repair if the rivets shear out than if the sheet metal fails instead. If the sheet metal tears out, you've got a much more complex repair. If the rivets shear out, you can usually do a cleaner repair, quicker repair. But as far as shear stresses go, the shear stresses tend to be fairly high for most of the materials that we typically use, up in this neighborhood for the most part. So it's not too bad of a calculation. Next time on Monday, we'll learn about safety factors, where we purposely assume the material is weaker than it actually is, so that we can build a little bit of safety into the system, so that if the loads momentarily go above what we expect, things don't tend to immediately fall apart. We never design things to be sitting right on the edge of what they can survive. We want them to have some safety margin there. So that's the shear stress we get here. Now, if all I've got are 5/8 inch bolts, this is the shear stress I've got if I've only got room for one of them. Any questions on getting the shear stress here? That making sense? Well, let's say we discover this shear stress is too high and we want to reduce it. Well, one of the ways to reduce it, the only two ways we've got to reduce stress, is we could either lower the force or increase the area. Now, one way to increase the area would be to drill this out bigger, put a bigger pin in, kind of like a snowblower, right? If you keep shearing through the shear bolts, just put a bigger bolt in. It'll be fine until your gearbox explodes. But you could increase the area that way, or you could increase the area by adding more fasteners. If we put another, let's just say we put another 5/8 inch bolt there, and maybe another one here. Now there are some
you've
details.
exceeded your transverse pitch.
Well, there are some details that we'll have to be concerned about in terms of the stresses, but that's a little bit beyond the scope of the class. You can't have them too close together. Edge distances, can't have them too close to the edge, can't have them too close together, or the stresses in the material become high enough that the material will tend to break. So assuming they're far enough apart, you can add the areas together. So if I've got 3 5-inch bolts instead of just one, I've got 3 times the area. I don't have 10 kips spread out over 0.30680. I can multiply that area by 3. So I take 30680 times 3. And get an area of 0.92040 square inches. And that'll cut my stress down. we get 10.865 KSI. So one of the very common techniques for adding area is not to go with bigger fasteners, but to go with more fasteners. And as I said here, as long as they're not too close together or they're not too close to the edge, you can just add the areas up. That reduces the stress quite a bit. So that's another important idea, and something that those of you who have been through sheet metal are more familiar with now, or at least understand why we did it the way we did it then. You don't want to just put one big rivet in the thing and have that hold it together. It's easier and more efficient to put lots of small rivets in. So that's another shear stress example. Any questions there?
If you put multiple rivets, that would multiply the area, not add them up.
It adds the
Oh,
area.
it adds.
Yep.
Okay.
It multiplies it by the number of rivets you've got.
Okay.
Because otherwise we'd end up with, like, inches to the eighth and things like that. You'd add the area. So it's rather than having one big rivet with that area, you can split it up into 3 smaller rivets with a third of the area each.
Okay.
As long as the area in total is correct, the area you're spreading that force out over, the shear stress will be right. In fact, to give you a little bit of preview of what we're going to do on Monday with shear stress and rivets, is we're going to figure out, we'll have this lap joint, we'll have how much force we need, and then we'll say, here's the shear stress the material can handle. So from that, you can figure out an area. You can figure out the minimum area of material that you'd need. And then you'd have to ask the question, well, how many rivets would that be? Well, if I'm using an 1/8-inch rivet, I know how many square inches that 1/8-inch rivet is. That's the area of one rivet. And then you divide that into the total area you need to tell you how many rivets you need. Round up to the next highest rivet, and you're good to go. So that's basically how the rivet calculations work. We figure out the minimum number of square inches of area we need to support that load without breaking things. And then we calculate how we can spread that out over a particular size rivet, whether it's an 1/8-inch rivet, whether it's -4, -5, -6 rivet. So that's shear stress there. Go ahead.
That being said, we're not going to have to worry about rivet spacing or transverse pitch, none of that. This is all.
Nope. No, we're not going to have to worry about
strictly
layouts or
hypothetical.
anything like that.
Okay.
That's more of an efficiency issue as far as keeping the repair small. In practice, well, in principle, if you had infinite space to work in, it wouldn't matter what you did as long as you didn't get close to those limits. So
Okay.
you want to put an inch between each rivet? Sure, go for it. Keep it, have a 10-inch edge distance. It's fine. It wastes a lot of material, but it's
Absolutely.
never going to be a problem from a stress point of view.
Okay.
But because we want to make things small, we want to ride those limits close, but not go beneath them. That's where we tend to ride a little bit close to that edge distance, usually not right on it. We want a little bit of margin there for future repairability and things like that. But the details of the layout only really matter when you get close to those limits. When you get as long as each rivet is far enough apart, you could shotgun the thing. It could look it could just be a whole bunch of holes with no pattern at all. As long as none of the holes are close to each other, it'll still work.
I just didn't know if that the spacing and the specifics that they want for everything have any bearing on how the material will take the stress or how
No,
it loads it, anything like that.
essentially, as long as you are past the edge distance and past the transverse pitch and the pitch and all of that, if you're a little bit above it, you may as well be inches or feet above it. It doesn't make any difference. As long as you're above the limit, you may as well be an infinite distance away. It doesn't make any difference. So it's just about efficiency at that point. All right. So, any other questions on that one? Now, one more thing to take a look at here. Well, we can do a couple more things actually. Let's stick with the lap joint for just a second. Another one that's pretty common. Another way of doing these lap joints, if we're dealing with, say, steel rather than aluminum. Another way to do a lap joint would be to weld it. And I'm sure you did this in welding at some point for those of you who have been through the welding class. So you guys didn't finish the welding class, did you?
No, we were
Nope.
right before this part.
So you do it.
No,
Let's
and
say,
their instructor sucks.
yeah.
But,
Well, hey, we're being recorded here, so
but I've made these kind of welds before, so
yep.
The
Yeah. So
instructor.
yep. If you're doing a flat lap joint, if we're doing just a single sided, we'd put a bead of well, we'd weld a bead here, let's say. Well, that bead is in contact with the surface by some amount of area. There's a thickness to this bead and a length to it. There's an area there. So we could figure out what the shear stress on that would be. So let's say we have our, we'll take that same 10 kips and put my top view back on here. We'll keep that 3-inch, so we got our weld there. Oops, I'm a little bit misaligned on my lines. Oh well. But we'll keep this 3 inches. And the width of this weld, let's make it a big weld. We'll make it a 1/2 inch. So there's a 1/2 inch. We'll make it it doesn't really matter what method, but stick is about the easiest when dealing with this kind of thing because with stick welding, you typically know from the stick you're using what the maximum shear stress is for that weld. It's usually encoded into the number for that stick. So if you're dealing with a 7,000 series stick, that's 70,000. That's 70 KSI typically. So you've got some idea of the maximum shear stress you can handle with that. So if we look at the contact area, and unfortunately, one of the things we don't do in the AMP program, but that I've done in other welding classes, is that if we would we do a weld and then we break it. You do a weld and then you clamp onto both ends with a load frame. You pull on it till it breaks, and you see where it breaks and how it breaks. If we pulled on this thing, what's going to happen here is it's going to break. It could likely break in this area. That's one of the areas we haven't gotten sufficient penetration with the weld. The weld isn't made with high enough quality. You can end up causing it to break there. Ideally, if you've done a good job here, it'll break somewhere else. We usually design welded joints so that the strength of this joint is larger than the strength of the basic material, and the material itself will break first. But if we were to draw a free body diagram of that top plate with the weld in there, what we'd have is shear stress right there on that bottom part of the weld. So that weld has a bead that's a 1/2 inch wide, or 1/2 inch thick, and 3 inches wide. So the area would be 1/2 inch times 3 inches, or 1.5 square inches. The force is 10 kips.
So Tom,
Yep, go ahead.
sorry. So we disregard the part of the weld that's on the upper portion of the material then?
Yeah. We're not worried too much about the tensile stress there, because at least where I've drawn this, how I've drawn the free body diagram, I've cut through the bottom portion. If I wanted to know the tensile stress right here, then I'd have to know something about the thickness of the material and the length of that weld to be able to figure that out. That could be done too, but I'm going to assume that that is not going to be the critical factor here in this one. But these sizes do all come into play when you design a welded joint. You do have to worry about which could max out first, and typically we get around it by making sure that the stresses here tend to stay lower than the stresses out here, so that the base material will tend to max out first. But if we focus just on the bottom portion of that weld, we'll have 1.5 inches, 1.5 square inches of area, that 10 kips, 1.5 square inches. So if we divide that out, so we get 6.6667 kips per square inch, KSI. So a little bit higher stress than what we saw with the bolts, but at least with actually it's lower stress than what we got with the bolts because it's spread out over more area. Now, for some reason, we figured that stress is too much. We could change things. We could change the force, or we could change the area. We could, in principle, make this a bigger weld, or we could add another weld. We could do a double lap joint where we put another weld down here. If it's the same basic size of that weld, then we've got two areas where stress is applied, where forces are applied, and we would effectively double the area. If we double the area, we cut the stress in half. So we go to 3 inches of area and then 3 1/3 KSI. So welded joints, similar idea. As long as we're clear on what the area is, it's pretty easy to figure out what your shear stress is. Any questions there? Now, one more to kind of break your minds tonight. Think about shearing sheet metal. If we take a piece of sheet metal, let's say it's 6 inches long and maybe 40 thousandths of an inch thick. If we wanted to cut this piece apart, we wanted to cut this piece off, we would have to apply a force to the surface that would make stress parallel to that exposed area. Essentially, if I were to draw a side view here, let's draw a side view over here. If I draw the side view, think about the sheet metal shear. You've basically got a couple of blocks where you're applying force, either up or down, sitting on a stationary block and then pushing down. That's creating shear stress right there. The area that is exposed when this breaks, that's the area that was resisting that shear stress. So, for example, here, let's say we push down with 10 kips of force. So we've got 10 kips of force spread out over this entire surface area. What would break would be this area that's 6 inches wide and 40 thousandths of an inch thick. The shear stress would be force over area. We've got a force of 10 kips. The area is a rectangle, 6 inches times 40 thousandths of an inch. So the area is relatively small, 0.24 square inches. That gives us 41.667 kips per square inch. Now, it's possible you've had this experience in cutting sheet metal. Maybe you try to cut it, but you just didn't push hard enough. What it means, and to get through the material, what that means is that you didn't create enough shear stress in the material to break through it, to break through that material and cause it to exceed its maximum shear stress. Now, of course, the way we really do it's a little bit different than this, but that's the basic idea of shearing through anything or punching through something. There's an example in the notes where a circular punch is used, which I don't know if I want to stick with that example because I usually bring in a little demonstration piece for that, for how I punch knockouts in electric boxes and things like that. There's a little circular punch, you dial it down, and it pokes a circular hole. Similar idea, except instead of using a rectangle for the area, you're using a cylinder, using the surface area of a cylinder. But same basic idea. The force you're applying is spread out over an area that is the thickness of the materials times some other dimension. Now, this is pretty high stress. Might not actually be high enough to break this material. Does anyone happen to know how it actually works on a sheet metal shear? How the metal's actually cut through? Do you cut down through the whole piece at once? I know sheet metal was a while ago, but
It's at an angle. It cuts it like
yeah,
like
yeah,
the
it's
thing
at
that
an
chops
angle.
off heads.
So rather than actually pushing down uniformly all the way across the piece, the blade, or at least the part that's applying force, is at an angle. I'm going to exaggerate the angle, I suppose, something like that. Look at what that does. Instead of applying that 10 kips of force over the entire area, it's applying that 10 kips of force right there on a fairly small area. What it's effectively doing is it's driving this area way down, because now it's only maybe contacting over maybe something about the thickness of the material. So maybe 40 thousandths of an inch by 40 thousandths of an inch. So you get a fairly small area, about so let's see here. I'm messing up on my calculator here. 0.04 squared. Yeah, 0.0016. That drives the shear stress way up, 6,250 KSI. This is why you can take even some relatively thick sheet metal, 63 thousandths, getting up into 10 gauge, things like that. You can cut through it reasonably easily on those sheet metal shears, as it's not trying to cut through the whole piece at once. It's just cutting through a little piece, and it gets that crack started and then just lets it ride across the whole part.
Just like a guillotine.
Sorry, go ahead.
Just like a guillotine.
Yeah, just like, yeah, you want to have that raked blade there. Otherwise, it would stop in the middle and it would be horrible. Well, even more horrible, I suppose. That's a lovely thought for the evening. Thank you.
My pleasure.
Yep.
I've been thinking about Cuomo all day.
Well, there you go. Let's see. How far are we away from guillotines? So let's see here. So that's another example of shear stress. So there's the punch example. This is similar to what I just showed here with the sheet metal shear. If you have a die block that is just a little bit smaller than the hole down here that it needs to fit in, you push down hard enough, this is going to poke through. It's going to shear out a section in the middle. And the shear stress, the area is going to be what area would be exposed after the part breaks. And that would be a circular area. That one's a little harder to do a calculation on. I wouldn't worry too much about that. But that's a circular punch. Now, I did mention that shear strain is a thing, but it's not something we tend to worry too much about, primarily because shear strain is hard to measure. But if you've ever tried to build anything like a frame or a box or a house wall, something like that, and you've applied a side load when you really didn't intend to, and the whole thing just kind of slid to one side or the other, and all the angles went from 90 degrees to something else, you've dealt with shear strain. But shear strain is about deformation in angle, not necessarily in length. And so it's a lot harder to really be useful in that sense. There is a model for it. There's actually even a shear modulus that describes how rigid a material is to shear stress, but it's not nearly as useful as elongation is with tensile and compressive stresses. So we don't even really bother with it here. So shear strain, yeah, there is a proportionality there, but we don't really need to deal with it too much. And we've done some examples. So that's our content here for tonight, shear stress and how shear stress works. Hopefully a few things from sheet metal make a little more sense now. But next time we'll take a look at materials. We'll look at where we can find the limits and what the limits mean for different materials. And we'll see how we can do some design with that. How to figure out, given a certain limit on the stress, what size do I want to set these things to? How big do I want to make these parts? How many rivets do I want to use to handle these loads? We'll also talk a little bit about safety factors and what the safety factor does for us. Anyone have any questions? All right. Well, if you're hanging around for the practicum session, we'll do some more practice on calculating shear stress. If you're not hanging around, check out the homework, and we're back on Monday night. Have a good evening.